So thanks everyone for coming. We'll get started. So today we're going to talk about media intelligence for the cloud using Amazon AI services. A lot of this will be about recognition, but there are additional services, obviously, that can be used to extend, say, deep learning pipelines for media in the cloud. So my name's Konstantin Worms. I'm a principal SA. I work on the media and entertainment team, and I'm here with Dean Perrine, who's a VP of Technical Solutions at Fox Networks. So we have an actual use case that I hope you'll find interesting. And just for the agenda, Dean will intro that use case, and from there on we'll talk about the architecture, the components that were used to build this, and then future-looking, what could be used to extend this going forward from a deep learning perspective. So with that, hand it over to Dean.
Hi there, I'm Dean. And as Con said, we'd like to talk about media intelligence, specifically enriching metadata and unleashing the value of content. Some of you may have heard of the company that I'm going to highlight today, as they've been around for a little while. As you can imagine, over the last 129 years, National Geographic has created a little bit of content. National Geographic has shown the world through wonderful imagery, video, and text publications. National Geographic also permits the user contribution of photos through applications such as Your Shot. There's one thing that we can be sure of, is that there will always be more photos taken than the year prior. In other words, there's always more photos uploaded and more photos contributed to the National Geographic archives. That being said, the opportunity. So as we migrate petabytes of images into AWS, we can ask ourselves, how can we then enrich our metadata once in AWS? How can we unleash the value of 129 years of content? As you can imagine, there's some differences in the metadata captured in 1890 versus 2017. So how can we create that baseline? So, for instance, some images may not even have any metadata associated with them, or it may be vague. How can we just create that baseline across all of our images in the archive? National Geographic has some unique challenges when it comes to automated metadata generation, such as niche image categories, where high confidence labels that are returned by recognition may not always equal high accuracy labels. How can we upscale images without introducing artifacts or noise, and upscaling for the purpose of recognizing what's in the image? How can we colorize black and white images with little or no historical context? Was the sash red or was it blue? We don't know, or recognition may not know. Speaking of historical context, for historical images, let's say of clothing or maps or structures that may not exist any longer, how can we then recognize those photos? Imagine trying to run the photo shown on top, the microscopic photo, through recognition. What do you think it would say? The expectation of National Geographic is that of a scientific journal. So you can imagine that high accuracy is required. National Geographic is undergoing a digital transformation. So they are migrating a lot of their NAS, FAS, SAN, LTO tape library systems that have images and video on them into AWS, onto systems such as S3 or services such as S3. They're transforming their editing and publishing platforms, let's say to run on GPU-backed EC2 instances and workspaces. Alongside the content, they're also transforming their video streaming, web, and mobile applications. And by doing this, the hope is to take advantage of next generation services such as machine learning and recognition. In other words, some of the cool stuff that Con's going to talk about next.
Thanks. So those of you that have used recognition know that there are a variety of options for processing media content, right? So if you're taking video clips, extracting frames, and then funneling those through recognition, or you have, like in this particular use case, maybe the vast majority of the content is image-based. and some of the content is then also media-based that needs to get analyzed. But if we look at the type, the content body, if you will, for which we're processing now, the important things are, for example, object and scene detection. A lot of the other features that recognition provides maybe as a secondary sort of processing phase in what we're doing. So say, for example, celebrity recognition or image moderation are not really key to this type of workload. But text detection that some of you may have noticed we released last week, this can be used for, say, historical context images where we can't identify landmarks, but potentially we can use OCR and text recognition to then do a secondary search, say via archives as one example. So if we break this down to the simple components of this pipeline, this is probably part of a larger pipeline, like a media supply chain pipeline, for example, and we're basically taking deep learning, metadata enrichment, and also services like recognition, and injecting them into the pipeline as the content flows through it. So there's obviously the notion of 129 years of content, but there's new content arriving every day. So we need to be able to ingest, store, then run analysis on that, and then deliver that content to, say, API endpoints, maybe business users or consumer users. So this section, I'm going to talk mainly about recognition and what value that provides here. So if you look at just the object and scene detection, which is the majority of the use case here, the important thing here is that for like a National Geographic use case, identifying objects like, say, skateboard or bench, things like that, there's use for that in terms of tagging metadata in, say, asset management systems. But really, the other things are also equally important. So recognition provides object detection and labeling with a confidence score, so I'm like 99% confidence that this is a shoe, but also scenes and concepts. So if you think of like a boat on water, it may tag boat, water, but then it may also tag a scene as being ocean, and then the concept as being sailing. So those like second and third dimensions are really important to be able to process those. It's also complex to know which concepts and words are actually scenes and concepts, right? And we can use natural language processing to extract that kind of data from all of the data that's returned by recognition. And then the other thing that's important is the service integration component. So if we're utilizing a managed service, that's given us this deterministic, consistent performance as we're piping all of this content through it. We want the labels to be returned within a certain amount of time. We potentially don't want to have to deal with downtime or blue-green if we have to retrain the network. So recognition abstracts all of that away in terms of that level of maybe deep learning, undifferentiated heavy lifting for the business. But you can see here there are a number of key integration services or services that work really well with recognition. So in this case, landing content on S3, utilizing API gateway, utilizing Lambda. So the entire workflow for something like this could be built on Lambda. And then for the things that we can't do that are sort of outliers, for example, maybe highly specialized deep learning pipelines, maybe it's a specific type of object recognition we need to do. We can utilize EC2 spot instances, AWS batch, and ECS to basically compartmentalize those and then have a second layer of processing after we've identified or maybe failed to identify some of the topics. And then the rest of these are fairly common from an architecture perspective. But you can see on the processing side, we released the elemental media services that just got released. So media convert and media live, if we're pulling in live streams, chunking them onto, say, for example, S3, or if we need to, say, transcode proxies of media files from an incoming mezzanine asset that may be high resolution, high quality, and we don't really want to process that with Lambda before sizing it down. So the other thing is, Rekognition has this use case in this pipeline, but it also has a use case across all of these other areas within M&E. So you can see things like if we're doing editing in the cloud, maybe our assets, we want to be tagged, the EXIF data, we could tag that data so that then artists or Photoshop editors can search against that using Rekognition to inject metadata into those files. The same with things like playout distribution and obviously analytics. So there's a high amount of code reuse here. The lighter boxes are sort of the pipeline that we're following here from acquisition to supply chain, archive, and then finally analytics. But you can see it branches out into all of these other areas too. And then if we look at where do we go from here, right? If we're using Rekognition, we're using it with AWS services such as S3, Lambda, maybe Dynamo for storing the labels for high performance that's critical to this. They're also key partners. Some of them are on the marketplace. Some of them have PaaS or SaaS offerings that can couple into this workflow. So essentially, we'd be handing off API calls to them to further enrich the data. And then there's also third-party software. So you could build those enhanced deep learning frameworks or build out those models on top of, for example, the AWS AI Army. Or we could utilize things like OpenCV, ImageMagick, FFmpeg, and others with Lambda as wrapped and encapsulated binaries. So really the thing is, why do this in the cloud as a managed service versus building everything yourself? You can certainly do that. There are lots of options for doing that. There are partners too. But part of the problem here is having full control over the entire content pipeline, and this may be for security purposes as well. But also, there are a number of points here. I think the most important here, and some which I described, is that you want a consistent response rate. So if we're versioning, if we're having to update infrastructure, it takes a lot of personnel to do that. So essentially, we're looking at solving 80% of the problem using a managed service, and then taking that engineering talent and applying them to 20% of the problem, such as the Lambda code or the additional deep learning models. So with that, to talk about the architecture, hand it back to Dean.
Sure. Great. Thank you. So again, circling back to the National Geographic use case, I'll quickly go through the media intelligence pipeline that Con had just mentioned and some of the requirements or some of the initial requirements that we came up with. So the media intelligence pipeline, I'm going to quickly run through the ingest portion, the analyzation of content, and delivery, programmatic delivery of that metadata that's generated. So some of the design requirements, obviously we wanted a system that would be self-service. So us being Fox Networks, a shared services unit, we wanted to make sure that anything that we're building for National Geographic could potentially be used for others in a multi-tenant fashion within Fox. So in other words, the metadata that we go and generate needs to be available via an API, programmatically available. We're also creating a method for it to be available through a web interface, manually searched as well. But the primary function was programmatically available so that it could be used by various applications or plugged into by various applications. A very large component of this, no pun intended, is the image resizing functionality, the automatic image resizing functionality. As Rekognition, as you know, has size limitations for images that it can process. And National Geographic, as you can imagine, has some extremely large images. Think of maps, for instance. Some of these are extremely, extremely large image files. Lastly, I'll dive into this a little bit more on the next slide, but we needed a way to have a unique identification of content as it passes through the system. So jumping into that for a second, needing to identify assets. So a naming convention method, especially if we're going to run this in a distributed fashion for multiple businesses, or even just within National Geographic itself, naming convention just doesn't scale. It doesn't work, and it gets tricky when you have multiple versions of an asset. Maybe they're named the same. So we needed a way to not only globally register assets as they pass through this system, so that we can understand if they've already been recognized or not, but also be able to see this down to the bit level in the actual images itself and not rely on anything else. A sidecar benefit of that is that inherently handles parent-child relationships of content. So as you have maybe a master asset and you have multiple file types underneath of that, that can all be categorized and registered as a single system. Next, the AWS components that we utilize to build out our system. As you can see here, we utilized recognition itself, obviously, and what I'd say is the second most critical function outside of Lambda that's doing a lot of the lifting here are the step functions. So actually creating a step function workflow to run this whole process. Lambda being inherently stateless, we needed something that could keep state and be the source of truth. And I'll dive into that more on some following slides. This is the solution architecture where you can see the components that we used and how they relate to each other. For instance, you can see we're using S3. As images land in S3 as part of the ingest process, Lambda is watching for S3 put objects. And from there, Lambda kicks off the step function workflow. The goal being that we get into that step function workflow as quickly as possible so that we're in a safe workflow place. We don't have all these peripheral Lambda functions with, let's say, SQS running and needing to manage all those components. We have one system, keep state, we have some failure recovery built in there. So, and lastly, pointing out, obviously, the UID. UID is something we built elsewhere in Fox we're reutilizing in this architecture. So sending a request through an API gateway to the UID to do that registration process. I'll dive more into the step function workflow now. Again, as Lambda is inherently stateless, we needed something that could keep state and act as the single source of truth for this process. So if you can see here the step function workflow that we're utilizing, where as an image comes in, we're checking to see if the image has ever had a UID generated for it. If an image has had a UID generated for it, we can then just check to see if it's been recognized, and if it's been recognized, we can go to, we can kill the process. If an image has not been recognized or there is no UID, we then skip down to the check size function, because we can be pretty sure if it's never had a UID, it's never been recognized because it hasn't been registered into the system yet. We skip straight down into check size. Again, recognition having a size limitation. If it needs resizing, we'll resize that image with Lambda. Pass-through recognition. As the data, the metadata circles back from recognition, we then simultaneously write to both Elasticsearch and DynamoDB. Note that we're not writing to DynamoDB, then replicating to Elasticsearch. We're writing to both simultaneously. The goal, again, to reiterate, is to keep as much within this workflow as possible and keeping everything tracked, keeping state of everything. The step function is your source of truth. Any information and metadata that has been retrieved through the step function is stored there forever, so you can go back and reference that. And I'll explain, some of the benefits of that a little later. Diving into a sample response, we can see we have a hawksbill turtle here on the left and the mountain gorilla on the right. The hawksbill turtle recognition has returned a 95% rating that this is a reptile. We're looking at sea life. There's a sea turtle here. It's a tortoise. For the mountain gorilla, a little higher rating, 98% that it's an animal, gorilla, a mammal, a monkey. So reasonably good labels that have been returned here. One thing to keep in mind, one thing we've seen, maybe not so much in these images, maybe a little in the gorilla image, is that with professional photography, the subject of interest may not always be center in the image. There may be various aperture settings, various focus settings, and so it may be a little harder to recognize, in which case you may need to pass off and actually just dial in on one part of an image and then upscale that for recognizing itself. looking at the storage of the labels that come back after we've received them from recognition. So this is an example of what we would store in DynamoDB, an Elasticsearch. You can see that at the top of this JSON blob, we have the UID listed there. So we know what the asset is that we're talking about, along with the confidence labels. One thing to note here is that what we're looking to do, we don't have in this version, but what we're looking to implement here is actually adding another section under UID, which is the workflow ID of the step function process that had generated this metadata. And I'll explain why that's interesting in a later slide. But just think about that, tying the asset ID down to the bits and the workflow ID along with the JSONs and storing that away. You could also utilize recognition's minimum confidence level. For the moment, we have it split off at 50% confidence to just go ahead and eliminate those false positives. No, there's not a truck in the turtle image or something like that. You know, you can just scrape off the last percentage there. Additionally, the max labels function for limiting the total number of labels you want returned if you want to have some constraint or boundary there. Client-side filtering obviously could be done as well. A little bit of the user experience. So again, we focused on the programmatic access of this data. So we're focused on the API, things of that nature. But we have generated an alpha interface. This is just an example of the alpha interface where we put a sample bit of content in and search for turtle. This is all done through recognition, so the recognition realizes this is a turtle, and then we can then see the labels that were returned there on the left of the turtle. So we're really thinking about how we can, again, maybe not so much this interface, but think about integrating this into a National Geographic mobile application or website where then you unleash all consumers to all of National Geographic's content, some content which may not have ever been surfaced before or may have been harder to surface because there was no metadata to really search about how to find that image. That's the goal, is really unleashing the value of all of this content that they have, because they have so much of it. Next steps. So I'm really excited about some of these next steps, particularly the video capability. We're extremely interested in extending this out, not only to video, but text content as well. Video is just a natural next step for this process. Next step, no pun intended for step functions, but it would be a next step in the step function process. Metadata transformer. So on the metadata transformer, we have various applications, various business units which may want this data. So we're looking at utilizing API Gateway to transform that JSON blob upon a request by a particular application or business into their expected metadata schema. So we can have varying output requirements. Recognition, so the result differential tracking is where I had thrown in the comment about keeping track of the workflow ID, so the step function workflow ID plus the UID of the content itself. So by keeping track of that, over time, obviously we're expecting that recognition gets better and better. By keeping track of that workflow ID, we can then, if image is uploaded, the same image is uploaded again, or if we're just cycling through and trying to feel out if there's any better recognizing capability. We could look up that workflow ID, look at the results that were passed back by recognition, and we could do a diff on that and just see if there's any difference. If there is, cool, tack that onto the end of that blob or integrate it in based on the label confidence levels. Goes without saying that we would want to integrate this within our web and mobile applications, maybe as a back-end engine to unleash that content and let it be viewed by consumers. Concept?
Thanks. So, if we look back at the original challenge, right, you can see at least one of these has been immediately solved, right? Ultra high resolution or high resolution, we can resize with Lambda. Potentially we could use something else if it was maybe 40, 60 megapixels, if you will. But how do we solve for these other problems as part of this workflow? And this is where, this is at least a very interesting set of problems to look at from the perspective of recognition. So I'm sure many of you that have built out a pipeline with recognition are often looking at these types of additional edge cases or foreign use cases. How do you solve that? What's the best way to do that? So especially like these niche image categories, maybe Mechanical Turk is a good option here. Upsizing the resolution, we could use some of the newer papers that have been published, for example, at SIGGRAPH, where we can take deep learning, use that to do edge detection, and then basically via deep learning interpolate missing pixels versus simply trying to scale up images and then apply smoothing or sharpening algorithm over the top of that, which doesn't work that well. The other thing is artifacts and noise. So we could use image magic to do noise reduction as an example, but maybe we could utilize deep learning to do more advanced noise reduction. So one of the byproducts of doing global noise reduction is that sometimes detail gets lost in the images, like in the particularly dark areas of an image if they have a high amount of noise. So maybe we can utilize some of the other advancements in the field to funnel that through a deep learning pipeline to do intelligent denoising. And then the other things like black and white footage, there are a lot of approaches to doing this now. Some of them are manual, some of them are automatic. A lot of the manual ones that have context to related data, we could use recognition tags and then process it. I'll talk a little bit about that in a later slide. And then this notion of high accuracy, right? The high accuracy is great, but it's not really great if the context is incorrect. So we don't want users to be searching a large archive and getting content back where potentially if they're getting thousands of images returned, that first page of thumbnails is potentially the wrong data and they have to paginate through to find the things they really want. So if we look back at this pipeline right now, we're really talking about deep learning over and the top of this existing pipeline that we have going with recognition. So you can look at recognition here as a feedback mechanism for us to be able to say, we got labels and it's a certain category, or we've analyzed these images and they appear to have sharpening or color gamut issues. Maybe we need to correct those via additional pipelines that we hand off to. And just to talk about this a little bit in terms of that last point, right? This is a great problem in that people can solve this. People can solve this fast, but interestingly enough, little children have problems with this. So I have two 8-year-olds. And I ran this through them, and they sort of, they'll nail it in about a second or 2 or 3 seconds. But really, as with a developed brain, a human will actually be able to tag these in about 200 milliseconds, that recognition of the shapes and the outlines and everything else. But it gets back to, is it artificial intelligence or is it assisted intelligence? And in some cases like this, it's a lot of assisted intelligence. So our algorithms will return back 99% confidence that this is a dog, but also 99% or 98% or something slightly less that potentially this dog is also a muffin. So that's a problem, right? And we can spend a lot of engineering time and hours, potentially months, trying to solve this, building models for this. But if we looked at something like, say, Mechanical Turk, maybe that would be a better use case for these edge cases that haven't been correctly tagged. And then looking specifically at Nat Geo, at like some of the photos, right? So the one on the left, you may, if you had a deep learning algorithm look at that, it may tag that as floorboards, or it may tag it as just lines, or it may tag it as railroad tracks. Part of the problem here is that This image may not have sufficient resolution to be able to dial down to, say, an 80-pixel boundary box around the cows that are in the feedlots. So we can't extract that information, and there's a whole bunch of permutations that make it too complex. The Regal shoes, this one is actually more easily solved now using recognition, OCR, if you will, or text recognition, where we're able to parse these fonts, potentially if they're hand-drawn, different font styles. And then also, you know, if they're skewed, if they're slightly rotated or tilted, it does a really good job on parsing that as well. So that's critical for these types of use cases where turn of the century, there were no fonts and typefaces. Well, there were, but you know, in many of these ads, people were drawing this by hand and then running it through printing presses. The other problem here is that you can see that there's a landmark, you know, around, say, New York. These landmarks have changed over the last century. So even if we extracted or try to run some deep learning algorithm to identify landmarks, it wouldn't successfully identify this. And then the last problem is, for example, the sunbathers. This is one of like pixel density and resolution as well. If we don't have sufficient resolution to dial down to, say, a towel, an umbrella, or a person laying on the beach, then this potentially looks like, you know, maybe a bunch of candy sitting on sand in terms of tagging it. So, you know, like Dean was talking about, going through this process of improving the image source in order to improve the recognition confidence of these labels. So one way that this can be done, or there are a number of ways to do this, which we almost consider now to be best practices because we see so many customers doing the same thing. The one is to stabilize the image, right? So we can use image magic filters. We could use binaries that are encapsulated with Lambda. We build them on, you know, maybe the Linux Army as 64-bit static binaries, and then we wrap them with Lambda, and we can then pass data to them, have them clean it up, return, you know, cleaned up images that we can then move back to S3. But, you know, if you look at like utilizing Python or Node or whatnot, a lot of the libraries that you may want to use, like ImageMagick, are already available for use, right? So you can then extend that with custom algorithms. So we could do things like highly specialized unsharp masks. So if you look at the bottom two faces, the one on the left has been improved with Richardson-Lucy, at least correction algorithm. And this is important because a lot of the default ways to do this that you may look at with, say, ImageMagick will simply emboss the edges of the image. And when you're doing embossing as like an unsharp mask where all the edges are sort of drawn out, that can give you false confidence scores. So things like the location of the eyes and whatnot may now be at the wrong places, right? Because you've repaired or attempted to repair the image. The other thing that we can do is we could wrap things like OpenCV. So if you think about maybe it's a really large photo that we're dealing with, maybe gigapixel in size, maybe we want to have some first pass to extract the faces. And there are a number of OpenCV algorithms. It's got about 2,500 that you can pick from. But there are a number of algorithms that you can use there to look at the pixel data and then extract the faces and then push those into recognition. And then the final important thing here, and this is probably the most important one, is being able to pass image data to recognition without any loss. So if you look at the top two examples there, so this extracted piece at the top there shows the amount of dithering in the scene. And you can see between the one on the left and then the one on the right, there's not much difference unless you really looked at the pixels. But this is an application of perceptual image compression. So in other words, we're keeping the resolution, we're keeping the data in terms of pixel data, but we're maybe dithering part of the images that the human eye doesn't really pick up easily on. So there are options that are open source, like JPEG, PNG Quant, Mozilla, MozJPEG. And then there are also commercial options such as JPEG Mini from one of our partners that also has options on Marketplace for that. But essentially, those can be used to size the images down without reducing the resolution, that we can then pass them into recognition without losing potentially the ability to tag or identify objects. So we looked at the service stack, right, in terms of if we look at the entire service stack, top to bottom, we have this notion of higher order services, and we talked a lot about recognition in the vision category. But then below that, we have a number of options for platforms, et cetera. And really, when we talk about this specific use case here, we're looking at deploying frameworks, and this could be TensorFlow, it could be MXNet, it could be Caffe, on top of infrastructure. The one thing that isn't pointed out here is that you can do fairly novel things, like some of the frameworks like Caffe 2 can be wrapped to actually be executed from within Lambda. So that's a kind of interesting use case for maybe text-based deep learning. And then the other problem is, if we have this infrastructure, where do we go? Where do we start with modeling this out to solve these edge use cases? Right, so if we have, we have this large image library, maybe we want to use that as our training data set, or maybe our validation or test data set for whichever deep learning framework we're using. We can actually start with some of the existing work that's been done. So if you look at the Places, MIT Places data set, there's about 2.5 million images of just different places around the world that have been labeled already. So you can use that as a way to train a new data set or create a new data set, but you start not having to create it from scratch. Similarly, if you had some kind of niche case for identifying celebrities or faces or whatnot in a crowd, there's a Celeb A data set, which is about 200,000 different images of celebrities. That's an open source one. And then what is almost the gold standard here is the CIFAR 10,000 or 100,000 labeled data set. So these are small pixels. The actual tiny image data set of unlabeled data is about 30 million images. But that's a lot of data that, when you're building these types of models and evaluating these use cases, you don't have to reinvent the wheel. And then the other thing here is, if we look at the infrastructure to run these models and train them on, what would be the best match for that, right? So there are a lot of instance families that you can choose from to run these deep learning, models on, for example. But as we release, say P3 versus P2, et cetera, there's a lot of improvement that comes in speed to, say, do inference or speed to train. But it doesn't mean that you shouldn't be using other types of instances, for example, utilizing Spot and diversifying across others. So this slide pretty much points to these instance families and good use cases for them, right? So if we look to FPGA, we have a partner there that has a marketplace solution that does 1 millisecond inference on images. So if we trained a niche use case and we wanted to batch a whole bunch of images through it, it's able to do about 900 to 1200 plus frames per second. So that's really interesting from that perspective, potentially if it's media files where we need to analyze every single frame really fast. And then there are other options here as well, right? So obviously, when you look at P3 and you're going to potentially 1 petaflop of performance, those of you that have followed the NVIDIA GPU roadmap over the last couple of years, about 2+ years ago, the training time would be about 30 days to train a layer of about, or at least a model of about 10 layers with X amount of images in a data set. And pretty much now this can be done in a factor of 8 hours. So it really changes the way that you can look at building, testing, and evaluating these different models and data sets. And lastly, the important thing is, especially with the P3s and other instances, if you do have, say, 10,000 or 100,000 images sitting on S3, you need both the EBS bandwidth to be able to hydrate that locally and then train the data set, Plus, you need the network I/O to be able to reach back and forth to S3. So you can see the scale here is fairly linear in terms of the capacity you get for network and EBS matching to the amount of GPUs. So that's really important for deep learning from this perspective. So getting back to, what about those edge use cases that we potentially cannot use, or maybe the engineering time is too high to actually build and spend time modeling this out for the niche use case. So the good option here is that Mechanical Turk can be utilized for these types of functions. So ImageNet was the most popular implementation there. But basically, what we're talking about here is building a UI, presenting that to as human intelligence tasks. So in other words, I present an image to someone that is a Mechanical Turker that's signed up. They're potentially paid maybe a penny, maybe more, depending on if they have specialized skills, to click through that, maybe select labels or type in a description. And the thing is, we know that if a human can identify an image at about, say, within 200 milliseconds, if we can optimize this task for this particular use case, where it's just clicking through and selecting labels, we can actually get a high inference rate from utilizing workers. So the next question is, how many workers can we actually get access to, right? So the graph on the left shows basically the population of workers. And this is a fairly old one. It's probably a year old or so. But the interesting part here is the darker, or at least the brighter green curves are actually people that have returned to do more tasks. So you can see there's a population that ebbs and flows, but you can potentially get 10,000 plus people working on a task if it's interesting enough. And how we'd present that is simply building maybe a web-based UI. You can see on the right example here. One of the things we have to do is we have to train the workers to be able to correctly tag the data, because we don't want them tagging data incorrectly. So we may say, if you've tagged X amount of images and we're happy with the scoring on that, and we do spot check QA, maybe there's an additional incentive for people that are doing this. So maybe they get paid more per task because they're really accurate at doing it, or maybe there's some other incentive. But essentially, the UI on the right basically allows people to type in a description. There are also hot links so that they can click. It'll take the image and maybe it'll do a TinEye search. Maybe it'll do a Google search, etc. Search the internet for keywords and so on, that they can then go and do research and use that to tag the image correctly. So optimizing for point and click versus having people context switch between using a mouse and actually typing in text is really important here. So back to our image archive, right? So if we look at these things that we identified, right? So these custom concepts, on the right-hand side is actually manual colorization. I'll talk about that in a bit. But if we look at these custom concepts, right, in terms of we're getting these tags back from recognition, what if we're getting plurals, singulars, different spelling, etc.? Maybe we're getting people, person. Maybe the tense is important. It's not that important for recognition. But if we're, say, processing closed captions, the text and the tense, past tense, present tense, etc., we need to normalize that. So there are libraries like Spacey that can be wrapped into Lambda, which allow you to normalize text, lemmatize it, in other words, reduce everything that is a person, people, maybe it's singular, plural, etc., into a single word. And from there, you can do things like do similarity scoring. You could say compare a dog, a cat, is this an animal? Those types of comparisons that you need to be able to drive more like intelligence into this pipeline beyond just the correct tags. If we look at the specialized categories, this is highly utilized, obviously, in things like manufacturing processes, right? So we take an existing deep learning framework, we tear down the last layer, and then we basically retrain it utilizing specialized images. So the interesting thing there is we don't redo all the training for things like detecting pixel edges and so forth. We're just doing transfer learning and then fine-tuning it for these highly specialized use cases. So it's one example of building on top of the shoulders of work that has been done already. The black and white footage is an interesting one. There are a lot of papers around this. A lot of the automated algorithms will colorize an image, but you'll see a sheen around the edge of objects. So for example, a person standing on grass, there may be a section around them that's not green. It sort of blends out to black and white. But this particular project here on the right-hand side, which is open source, it basically allows you to tag different parts of an image, and then it colorizes it based on a semantic theme. And that theme is derived from what you can see on the bottom side. We could use labels coming back from recognition for that. So we may use the scene label, which is potentially outdoors, and then pair it with another image that's been trained for outdoor colorization. Or potentially we could take the tag for a bird and then train this to recolorize with another image of a bird. So these are two options to get higher quality colorization of content that was potentially black and white with no context. The low resolutions we talked about, so this is a classical scaling problem where we're actually upscaling and then interpolating the difference instead of just trying to stretch and add more pixels, which just leads to a blended out picture with less detail. And then the niche and historical context, like I said, the important thing here is to use things like potentially OCR to identify labels and then search outside of the image context, or to utilize crowd working like Mechanical Turk. So getting back to how this is all put together, right? So the pipeline that Dean talked about has a lot of Lambda step functions, etc. But key to that is that the content lands on S3, gets processed by Lambda, and then lands on S3 again. So potentially we can use, for example, multiple buckets. We could use auto-scaling groups. Each auto-scaling group has a different deep learning algorithm to look at different bucket locations. And then we use the simple S3 event triggers to then funnel that into, say, SNS queues to go off and analyze this image using a different type of deep learning infrastructure, for example. So that's an easy way to expand that, where you're having to use things like, say, the AI army, for example, and set up auto-scaling and so forth. So this basically is at the core here, or the crux, is a feedback loop on training and then identifying and then funneling that data to customers or users, and then potentially having them provide feedback into the system. So, from the perspective of the pipeline, then overlapped on top of this. Lambda obviously is key to this, right? So we'll utilize for our data scientists, or those images coming in that we're going to train would land on S3. If they're unlabeled, potentially we need to get them labeled, and we use Mechanical Turk to generate that ground truth for the training data set, which once we've trained it, can go back into S3, potentially a different bucket, maybe different security, because this is now classified as intellectual property, so we'd want to encrypt the assets, have separate buckets, lock it down with IAM, etc. And then EC2, right, so this would be our trigger to process using these other models. And then finally, the same API gateway, because we can do multiple targets for endpoints, could look at a different location for that data, or maybe a different table in, say, Dynamo as an example. So Lambda functions and step functions are key to all of these, right? Eventing off S3, processing the images, maybe labeling and putting the data into Dynamo, and then a feedback loop, which can then power these other deep learning processes. And then the final delivery, obviously, to S3 with Lambda for additional processing, as the API calls come in, maybe we want to do authentication, etc. So, to sum up.
Right. To sum up, there's no magic bullet, as you can see, that just passing images off to recognition may not be sufficient, right? So let's say, as Con was showing the picture of the image with fog, maybe the first step in your step function workflow is to pass to recognition, identify that there's fog, then programmatically say, all right, now that I know there's fog, let me send it to my tool that I know can remove fog without embossing, then send it back to recognition to re-recognize, then use that data and move forward. So you may need to do layering or have a layering approach to getting your results back. Or even additionally, if you really can't recognize within the image, think the microscopic image, for instance. I mean, come on, you may need to send that as a step in your workflow to Mechanical Turk and have someone who's specialized in that actually identify what's in that image to get those results back. It's really, the focus here, as I mentioned, National Geographic, Scientific Journal, we need high accuracy. It goes without saying that you'll want to get the right people involved. Image specialists, data scientists, coupled with your DevOps team and developers to really make this successful. How do you know what happens to an image when you scale it up and do selections and make sure that there's no artifacts and noise? How do you reduce that in an image? It goes without saying as well to not overcomplicate the infrastructure in the pipeline itself. As I mentioned a couple times, was really trying to get things within a safe workflow, within a step function workflow. So you have something that's scalable, reliable. It's a single source of truth. You don't have to go hunting around into ES or Dynamo to retrieve results. You can go back to one location. Just really follow the KISS process. Keep it simple.
Yeah, and the key thing there is utilizing the managed service to solve 80% of that problem. So at least on the media side, we deal a lot with customers that are utilizing services such as recognition. And in many cases, the problem will get attacked at the development level by, it doesn't do function X, we should just build this custom. But the problem there, like I said, is training that, versioning it, keeping it up, doing the blue-green or red-black deployments, etc. It takes a lot of time and man-hours, especially when you're training against, say, data sets that, for this size, you may need to utilize that entire 30 million tiny image data set to have high accuracy, which is a lot of storage and I/O against S3, hydrating the content, training it, potentially pulling it back on-prem, if you have clusters of, say, 1080s or Tesla cards or whatnot that the data scientists are using. So solving that 80% of the problem using recognition and then focusing on those smaller things, either by building them with those teams or by using some of our partners like Grey Meta, et cetera, that specialize in that. And then lastly, the compute diversification that I talked about, not everything has to run on a P3. Some of the other instance families work really well, especially things like the natural language processing. You can do, like, say, inference on a bag of words in about 800 milliseconds on an i5 CPU. So you don't even need a GPU for that, and you can potentially look at wrapping that into Lambda to even reduce the cost there. But utilizing FPGAs and then especially object storage is the key to all of this, along with, if you have to use instances, do it on spot because inference is fast, and if your spot instance gets terminated, you'll just pick up and resume the next job. You potentially won't have an interrupted job there. So with that, thanks. And there are a couple of related sessions as well. So around OTT, we also have a couple others on recognition, more deep dives on that. And then there are a couple workshops around this as well. So we'll take any questions.
You got one over there. Go ahead.
Hi. Are there particular deep learning frameworks that you would recommend for, say, news media or sports media, or does it matter?
I think you have to look at it from the perspective of, depending on the framework you select, I'll just repeat the question. Are there particular frameworks that work better for, say, news media production, right? And that could be things like motion graphics. So on the one side, you can look at some of the developments that are being done to, say, track people in video frames. In other words, the optical flow, where are the players moving on the field, et cetera. There's a lot of research in that category, but as to the actual framework that you deploy on, it doesn't really matter, but a lot of the frameworks out there like Caffe, MXNet, et cetera, we don't have a recommended framework, but if you look at it from the perspective of how can I get going quickly, the two options there are using, like Caffe has a model zoo, most other frameworks have a model zoo as well, that you can find a model and then fine-tune it. But the other option is we also have now a group within AWS AI Labs that will actually, from that perspective, help build out those models for that use case. Any other questions?
One question over here.
Yeah, so the question was, what about NLP, basically, right? What's going on around that? So I mentioned one framework, Spacey. That's actually really high performance. It allows you to load custom models for different languages. And you can do the same kind of confidence scoring that you can do with images with Spacey. There are also additional frameworks that have been built on top of that, such as Textacity. The underpinnings is scikit and other Python libraries, right, for this. So they're higher order. But they'll do things like you can compare, say, a banana and a dog versus a dog and a cat, and they'll give you a confidence score that the one is an animal, but the other ones aren't. And you can do that within Lambda. There's a process to package it correctly, compile it, reduce the binary size. Like one of the other sessions, I'll talk about doing that. But essentially, that's a really good option for doing that.
Yeah, that's one thing that we're looking to do with the next step after we generate the labels, is actually run NLP on top of that, and then get those results and then tag those back into that same blob. So we have, mammal, monkey, sea turtle, and then, run NLP on top of that and have it maybe generate a string, a sentiment of what this is about.
Yeah, if you look at labels coming back from recognition, that's the simplest kind of NLP use case you can have, because you're simply comparing terms, right? We're not having to do topic modeling or anything like that. But the interesting use case is if you do have something that potentially there is an image and there's a lot of metadata as sidecar data that's been supplied with that, or potentially it's media and there's closed captions, you could use those same libraries to normalize the words and do topic modeling against that. So that can then be further used to accurately categorize that data if you have text data to go with it. Any other questions?
One right here.
Do you have any challenges with using any of the services, like for example with the step functions you are writing in parallel to the event search and the DynamoDB? Did it handle the path scenarios fine, or were there any kind of things to look out for previous or whatever?
I think that's just kind of a core function of the step functions themselves, right? So you can run a lot of things at once and really handle the parallel processes. And so we really, yeah.
Thanks.
All right, thank you.
So, yep.